All right, good morning, everyone. On behalf of NASA Land Cover and Land Use Change Program, I welcome you all to the Impacts of Regional Conflicts on Land Cover and Land Use Change webinar series. My name is Allison Thiem, and I'll be moderating today's webinar. This is the 8th and final webinar in the series focused on research of regional conflicts on land cover and land use change, including several NASA LC-LEF projects. Before we begin today's webinar, I'd like to go through a few housekeeping measures. Today's webinar will be recorded and it will be available online via our website. A question and answer session will be held after the presentation. If you have any questions for our speaker, please share them with me via the chat box in the lower right-hand side of your screen. We highly encourage your active participation throughout the session. In case of any technical difficulties, we'll use the chat window to directly interact with me, and please note that we will have all participants on mute to avoid any background noise and interruptions. There's a wealth of information available at our website, lcluc.umd.edu, about our past and present projects, science team meetings, previous webinars, and a variety of land cover metadata generated through our projects, and we invite you to visit our website to know more about our program. Today's speaker is Mr. Victor Olsen, who is a early career scientist and a geospatial consultant. He has a master's degree in geoinformatics and remote sensing from the University of Copenhagen and has worked as a consultant for NIRIS and currently works with the REACH initiative. Mr. Olsen is based in Amman, Jordan, and his research focuses on using remote sensing to study drought, agriculture, and water resources. And today he will be presenting the impact of conflict-driven cropland abandonment on food insecurity in South Sudan, revealed using satellite remote sensing. With that, I'd like to hand it over to Mr. Olsen.
All right, thank you, Allison, for that introduction, and also big thanks for inviting me to partake in this this series of presentations. And thanks everybody for attending as well. As Allison mentioned, this will be on the topic of remote sensing, conflict, and food security in South Sudan. If you have any questions that I won't be able to answer today, please do reach out on my email or through my website, victorolsen.com, and I'll try to attend to those questions after the presentation. All right, we'll dig right into it. Let's see if I can change slide here. This presentation will be centered around a recent publication in Nature Food titled "The Impact of Conflict-Driven Cropland Abandonment on Food Insecurity in South Sudan, Revealed Using Satellite Remote Sensing." Big thanks here, of course, to my co-authors who really made this happen. We have a group here of really talented academics as well as food security specialists. This paper in brief is really about establishing a link all the way from remote sensing observations of cropland through potential drivers of changes in cropland, all the way down to an impact on food security on the ground. So there's a bit about remote sensing. There's a natural experiment, and there is statistics on nutrition and the impact on food security in South Sudan. We'll be digging into this over the next half an hour or so. First, a little bit of background around why this is an interesting topic to research to begin with. First and perhaps foremost, food security is still a really big issue around the world. There's over 800 million people that are food insecure. And this number is not really changing. At least in the last couple of years, this has remained fairly stable. We can also see that food insecurity predominantly happens in areas that are also plagued by armed conflict. So there's this linkage between food insecurity and conflict that's really important to understand in order to get to the root cause of food insecurity. In addition to that, it's also really important to get a grasp on the local food production in these regions, especially because a lot of these areas are reliant on subsistence farming. It's often smallholder agriculture. But getting these estimates on local food production can be extremely difficult, particularly if it's remote regions, and of course if it's regions that are plagued by conflict, making access very, very difficult. Finally, in fact, most of these regions and countries that are affected by food insecurity and also armed conflict in combination are located in sub-Saharan Africa. South Sudan is one of these regions that's especially challenged by all these three things, really, including difficulties of accessing or getting a good estimate on the local food production. South Sudan is therefore also the region that we'll be focusing on in this study. With that as the background, we'll dig into the core components of this study. There are basically three things going on in this study. First of all, we have the remote sensing sort of pillar where we produce cropland maps. We do this to find out if cropland abandonment had happened in the so-called green belt of South Sudan between 2016 and 2018. So here we apply a remote sensing approach. We classify satellite data to produce these maps and get these numbers on cropland abandonment. That's sort of the first core technical component. Then the second part of this study is essentially a natural experiment. So here we set up two groups, a conflict group and a non-conflict group, in order to isolate conflict as a local driver of cropland abandonment. And then we also try to quantify the impact of conflict specifically on the changes that we can see in terms of cropland abandonment. The final part of the study is on kilocalorie losses, where we take a step further, essentially going from an estimate of cropland abandonment, or sort of the area that we can quantify, to what that means in terms of food insecure people on the ground. So how many people could have been satisfied with the kilocalories produced in the areas that we see have been abandoned. And so in doing so, we then go all the way from these cropland maps down to an impact on the ground. At least that is what we intended with this study. Okay, we will dig into each of these components in a bit more detail, starting with the remote sensing part on the cropland maps. This right here is sort of the challenge that we are dealing with as when we're trying to quantify cropland using remote sensing. This is an image taken over South Sudan. This is a very characteristic landscape for the southern green belt, which is this productive zone, very productive agricultural zone in South Sudan. What we see is subsistence farming that is reliant on human power, rain-fed fields, very small field sizes of irregular shape, very little animal traction. So it's pretty much all human powered, multi-cropping throughout an agricultural season. In addition to that, it's also a very cloudy environment. And these things in combination make for a very challenging environment to classify cropland and quantify cropland abandonment. That is nevertheless what we attempted to do in this study, and I'll take you through the techniques that we applied in order to do so. First of all, down in the bottom of this slide here is a link to the repository where all of this code is available. Everything is scripted in Earth Engine, this cloud platform, so it can quite easily be replicated. Please do take a look at that to see if that's something that you could use for your own research. All right, so the first sort of key ingredient to making this happen, to classify cropland and quantify abandonment, was for us to use multi-source input. We essentially wanted as many cloud-free observations of land cover as possible. So we used a combination of Sentinel-1, the SAR data. We used Sentinel-2, 10-meter resolution optical data. And then we also use Landsat 8 and MODIS. We then, in addition to capturing as many observations as possible, we also try to get a full calendar year in each classification. So getting the full seasonality across a year was really important. And we did this by producing mosaics. We essentially turned our optical time series into monthly mosaics, so we got 12 mosaics across a year. And this was really important for capturing how different land covers change over time and for differentiating cropland from non-cropland land cover. We then also used data fusion, and I'll talk a little bit more about how we did that. We have a figure here that helps exemplify this approach. Essentially, the challenge that we were facing was that when you produce mosaics using Sentinel-2, Landsat 8, or MODIS, you do get quite a significant amount of gap from cloud coverage. There's simply not enough satellite images taken across any given month to ensure that you always get cloud-free observations, even when aggregated across a month. So our approach to dealing with this was to fuse these three optical datasets into one cloud-free 12-month composite, or rather 12 monthly composites across each calendar year. On the left here, we see a Sentinel-2 monthly composite, the green pixels representing cloud-free NDVI observations, and the white pixels here representing gap from cloud and cloud shadow. So we use the Sentinel-2 time series as a starting point, and then we first filled in gaps with Landsat 8 whenever Landsat 8 observations were available. We did this after calibrating the Landsat 8 observations to make them more, let's say, appropriate for data fusion. And then when there were no other observations available, we used MODIS to fill in the remaining gaps. And the result is this neat 12-month time series without gaps. Right, then we also applied feature selection for optimizing the inputs. Our layer stack had grown fairly big with 136 features from these optical data sets, but also from Sentinel-1. We also had included some seasonality metrics and a few other things. And essentially, our approach to this was we are fine using any observation that is useful for differentiating these land cover classes, but the challenge is that it's hard to know exactly which features are important, which NDVI composites are important during a year, or which data sources are even important for a given year. So we applied a feature importance calculation using one of the scikit algorithms. We could then observe that accuracy sort of plateaued around 60 features. And then we simply just took those 60 features and used only those in our classification. So this significantly reduced the amount of input data and really allowed us to classify using a lot of data, but not too much for the algorithms to take forever. And also always selecting the most appropriate input features. All of this, as mentioned, was done in the Google Earth Engine. This is really, in my opinion, an absolute game changer for these types of problems. We were able to run everything in the cloud remotely. Some of these classifications took over a week to run, and this would have been very, very difficult on a local machine. We ended up using over, or at least evaluating over 7,000 images for each classification. So this is really where Earth Engine is a very valuable tool. In addition to that, we also used over 4,000 training data points to classify. This included field observations collected by the WFP of active cropland for several years. And then we had also augmented this data set significantly with remote observations. Here I should mention that we used the Planet Explorer tool, which allows us to step through worldview base maps. I believe it's worldview base maps. At least we step through planet base maps. And they have set up these monthly mosaics you can step through, and in doing so, you can quite easily differentiate a lot of different land cover types, which really helped us augment this data set with non-agriculture land cover samples. Absolutely vital in the context of South Sudan for this particular problem. Finally, we then trained and applied a random forest classifier. So this is sort of the setup, and it worked quite well. We achieved accuracies between 69 and 80% overall accuracy for these classifications. Yeah, we can talk a little bit more about how this might be optimized. A few of these things are already getting a little bit outdated. At least there are things that can be done much better today. So there's a lot of potential in optimizing these types of classifications. All right, that is the cropland methodology. Then this yielded 3 cropland or 3 land cover maps across 3 states of South Sudan, the lakes, Western Equatoria, and Central Equatoria. You see where they're situated down here. As mentioned, this is the green belt, so-called green belt of South Sudan. It's the most productive agricultural zone in the country, so it's very important for food production nationwide. We'll step now into having a look at these subsets here, A, B, and C. But here I'll just say there were a couple of regions that we excluded from our classifications because they proved very difficult to accurately classify, but otherwise we managed to get pretty even accuracies across this region. Yes. So this is a closer look at these classifications. We have examples here from the lakes, from Western Equatoria, and from Central Equatoria. And the patterns we observed were that there was a general increase in cropland in the lakes. I should mention here that these red pixels represent 10 by 10 meter cropland observations. So we could see an expansion of cropland across this region between 2016 and 2018. Whereas in the Western Equatoria, we saw cropland abandonment in this same time frame. Here, for example, we can see how the cropland extent reduced, whilst bush and forest expanded into previous cropland areas. Similar observation here for Central Equatoria, with quite a significant reduction in cropland, especially between 2016 and 2017. These maps were then used to quantify the total cropland abandonment. We quantified that as 89,000 hectares across these 3 states. Yes, and then having these data sets, we were then able to essentially measure and quantify cropland abandonment at any spatial scale, which is then basically what we use for the next step in this natural experiment. Yes, maybe I should just emphasize here that in this particular case, when we talk about cropland abandonment, we're essentially talking about a change in the extent of the cropland area within any given spatial unit, so a state or something like that. Yeah. Okay, we'll jump over to the next section of this study, which is the natural experiment. Here, the purpose of this was to assess the impact that conflict specifically has had on cropland abandonment. The issue, or the sort of the challenge with doing that is that you cannot, of course, simply compare areas that have been affected by conflict with areas that have not been affected by conflict, since there are confounders in these samples. One approach to dealing with this problem is that of propensity score matching. This paper here explains the statistics behind this really well. I would advise having a look at that. We'll be going through how we applied the techniques in our study, but do have a look at this if you're interested in applying it. I'll just say for now that it's essentially about reducing the influence of confounders in your sample groups so that you can compare your two groups as though they were randomly sampled. Now, how did we do that for our particular use case? First, what we did was we found data on conflict. Here we use the ACLED dataset. This is a global dataset, a georeference dataset on conflict events. It offers data around the world and was the best that we were able to find for the case of South Sudan. As I mentioned, this is a spatially explicit dataset, which is very important for this particular use case. We then filtered this dataset temporally. Essentially, we selected conflict events that had happened between agricultural seasons that could then be associated with a change in cropland extent or cropland abandonment between these two seasons. Having done that, we then sampled areas that were not affected by conflict. So we see here then are the red points, which represent areas that were affected by conflict within this sample period, and the green polygons here are then areas that were not affected, randomly sampled. The challenging thing then is how do we then subsample these datasets so that they are comparable? And this is where propensity score matching comes in. Essentially, what we do is that we set up a model that can predict the likelihood of the occurrence of conflict. We did this using a logistic regression model that was applied or that was modeled on a couple of different explanatory variables. This included distance to roads, distance to settlements, and also population density and pre-existing cropland area. So these 4 explanatory variables were able to predict the likelihood of conflict within the conflict sample quite well. And then the principle here is that if we apply that same model across the conflict points as well as the non-conflict points, then we can do a subsample on points from both groups that have the same likelihood of the occurrence of conflict. In doing so, we have turned this into a sample that's comparable to a random sample. And when that is achieved, we should be able to measure the impact of our phenomena, in this case conflict, simply by comparing the mean of the two groups, the mean, in this case, of cropland abandonment within the two groups. All right, that's quite a bit of information, but that's essentially how this workflow looks. And as I mentioned, it is much better explained in some of our references in the paper. I'll come back in the end to what to the results we received from this analysis. Right. The final sort of pillar of this study was then that of kilocalorie losses. So at this point, we have quantified cropland abandonment. We have looked at one driver and quantified the exact influence of that particular driver on cropland abandonment. And the last step here then was to calculate what that means in terms of lost kilocalories and people that could have been met by those people whose needs could have been met by those calories. We did this using statistics on expected yields, on expected crop types. Since we had only classified crop or non-crop, we had to convert that into an estimated crop types as well. And then we also use data on nutritional needs in the region. And combining these data sets, we then were able to quantify the number of people that these abandoned lands could have satisfied. All right, to the conclusions, and this is my last slide. From the first section of this study on cropland maps and remote sensing, we were able to deduce that it is possible to map smallholder cropland in this region, at least with accuracies between 69 and 80%. This in itself is something we were quite happy with. It's a very challenging environment to map cropland. I will say though that today, now we're about 2 years in, it's about 2 years ago that we did the actual classification, and quite a lot has happened since then. So I think there is a lot of room for improvement in terms of accuracies and also sort of spatial detail that's possible with this kind of method. Nevertheless, that was one conclusion. We could also conclude that cropland had declined by around 16% across our three states that we observed. Declined from 358,000 hectares down to 299,000 hectares. So this is quite a significant reduction that has likely had a severe negative impact on food security. From our natural experiment, we could deduce that there has been a substantially larger reduction of cropland in close proximity to armed conflict. Now, and what we're talking about here is a local impact. Essentially, if you're between 5 and 10 kilometers from a conflict event, or if a cultivated area is between 5 and 10 kilometers from a conflict event, there's a very likely reduction of cropland within that region. We quantified that as 17%. Essentially, we could deduce the conflict explains 17% of this cropland abandonment observed. Yeah, so that was the main finding from our natural experiment. Yes. The final part of the study was then the kilocalorie losses, and here we quantified that around 106,000 tons of food was sort of omitted through cropland abandonment, and that this food could have satisfied around 320,000 people in the region. And again, given that this region is very much reliant on subsistence farming, it is very likely that this has had a severe negative impact on food security in the region. That is it for my slides. Again, do check out the code on GitHub if you want to replicate some of these findings. We have both the classification code from Earth Engine available there, and also the code we use for the propensity score analysis. And please do reach out if you need any help replicating or scaling that code in any way. Thank you. I'll hand over to you, Alison.
Great, thank you, Victor. Thank you so much for the wonderful and informative presentation. We will now take some questions, and I'll read those out from the chat box. So as any of the participants want to send in their questions, please feel free. And we've got an additional panelist, Dr. Pristupov, joining us for the question and answer session as well. So if you have any questions, please send those in. It looks like we have one question to start with. This one is from Hannah Kerner. They ask, they say, thanks for the excellent talk. It looks like you estimated crop area change by differencing the area estimates from each individual year. Why did you choose to do this instead of making a change map and doing the area estimate of change directly? Since one downside of differencing annual estimates is that you could have a higher error due to having to add the standard errors in your difference estimate.
Yes, thanks for that question, Hannah. I think one challenge with the alternative method there is that there's so much shifting cultivation in this region. Basically, every single agricultural field changes from year to year. So we found it necessary to sort of quantify the actual change in area within a given spatial unit in order to really capture the reduction over time, if that makes sense.
Can I also add, as Alexander, in response to that, I think also the discussion goes that there are two ways how to perform the change. One is that we have post-classification change detection, and this way we multiply the errors. And this is actually the way we went. Another way is that we classify the change. So it's one of the classes would be the change. Yeah, so that's another option. In that way, we reduce these errors. The reason why we went with this multiplication of the errors, because our training data were coming from the World Food Program for each individual year. So we didn't have the results on the abandoned lands, but rather we had the results on the cultivated crops, grasslands and such for each individual year. Since this area is quite, I would say, danger in visits as well, so we're very happy that we had such a wonderful training data right from the ground. So this what it limited us to use, sometimes it's called layer stack change detection analysis and such. Thank you.
Great, thank you for that. At this time, it looks like we don't have any more questions. So does anyone else want to chime in here and send in some questions? We'd be happy to respond to them. I'll give you all a couple minutes. Oh, looks like we have a... so Hannah would like to be unmuted so she can ask the question herself and clarify. You are unmuted.
Can you hear me?
Yes.
Okay, thanks. Sorry, it was getting kind of difficult to explain in the chat window. So I understand what you're saying, that it's the labels you have are for individual years, so it makes sense to create the maps for each year and then do the area estimates within those. So what I was asking was, another way would be to create your map still for each individual year, compare them to get the change map, and then you estimate the areas in the change map based on, I'm assuming that you all like did a reference sample that you labeled and adjusted your map-based areas using that sample. So if you were to do the reference sample based on the change map, and then estimate that area. Because, for example, in the second bullet here, these two area estimates for 2 different years, if you subtract those, then your plus or minus standard error would become potentially higher than the change area, correct? Maybe my question's not clear. Let me know if it's not.
Thanks. I thought I was unmuted there. Thanks, Hannah. Yes, that's clear. You're absolutely correct that there's quite a substantial error margin here that should be considered when interpreting these results. And what you're saying here, I'm just trying to wrap my head around the alternative here, is to map the change from, for example, cropland to non-cropland, from one year to another, to sort of classify that directly. Instead of classifying cropland area, we're simply setting up an image classifier that classifies a particular type of change. And in doing so, we won't have these double standard errors. And why didn't we do that? I think I mean we did look into options like these. I think one of the issues is basically what Alexander was also saying, that it's very difficult to create a good representative large training data set of changes in cropland. Would require that you observe the same field twice, which is of course very difficult to do in the field. It could perhaps be done if you are reliant on remote observations, but even then it might be a little bit difficult. So I think the main reason for it was really that it's difficult to classify, at least for this particular environment. It was quite difficult to classify change directly. Does that make sense, Hannah?
It looks like we have an additional comment from Dr. Pontus Olafsson, who wants to chime in here, so I'm going to allow him to do that.
Hi, Victor and Alex. Nice to see you. It's Pontus here. So I'm a co-author of this article, and so this is an interesting question that we were discussing when we were writing up the paper, and it's a question that is relevant in many other contexts as well. When you're interested in change, it's a very, very small proportion of the landscape. Are you better off trying to map that change directly and define a stratification accordingly? Or are you better off doing it the way we did it here? And I'm not sure there is a good answer to that question. I think we need to do more research on that. At the end of the day, we are estimating the areas by sampling. And so the mapping effort here is mainly to create strata or to define strata. And we've been wrestling with these issues in the Amazon, for example, studying the expansion of the deforestation frontier in Colombia, where we have very, very similar issues, and the change tend to be minuscule, especially on an annual basis. And when the change is that small, you're going to need a very large sample to properly estimate it. And any like errors of omission, for example, tend to be very, very complicated in those contexts. So I'm not sure what the best way is to do it. I think I would really like to see more kind of targeted investigations into these types of issues. And I think there are different ways of doing it. I'm just not sure which is the best way of doing it and which is the most cost-effective way of doing it. I mean, we could try to spend a lot of time identifying these areas of change, cropland abandonment, and then define strata accordingly and collect very, very large amounts of sample data. And that might give us a better result, but it would also be much more time consuming. And again, this is a problem within like the REDD+ context where people are trying to estimate the area of deforestation and other carbon emitting activities on an annual basis when the areas are very small. And so this is a very interesting question. I think we just simply need to do more research on how to best do this type of work.
Hannah, did you want to respond to that?
Yeah, thanks. Sorry, I don't want to take too much time with this one question. But what I was asking is kind of a mix of those two things. So you would be classifying crop and non-crop in each map, and then you compare those to get your change map. And then Pontus, as you said, your area estimates are based on the stratified samples that you get from the map, right? And so you would do the stratified, you would use those change strata to get the samples and then do the estimate. So you're not classifying with your model the change classes, but you're comparing them to get the change classes. So I guess I'm seeing it as kind of three different ways to do it.
Do any of our panelists want to respond?
Yeah, no, I agree. There's several different ways of doing it. You could try to map it directly. You could do post-classification comparison to get the. There's a couple of different options. You could try to resort to just sampling, and I don't think any of these are right or wrong. None of these approaches are right or wrong. They might be more or less efficient though, and I would love to see more study. I mean, the focus on this study was not to investigate these types of issues, but it would be interesting to investigate these types of issues that we're discussing in contexts such as cropland abandonment or any other change processes that are a very small proportion of the landscape.
Thank you for that. I think we've answered that question as fully as we can for today. I would like to move on to another question from Rahul Kashyap. What is the best VI, vegetation index, to detect changes in cropland? And is there any available food production data in spatial format?
All right, thanks for that question. Food production data. All right, so regarding the first question here, there are, of course, several indicators of vegetation that can be used. I think what we did in this study, as mentioned, was that we tried to capture the full seasonality. So we tried to capture or include NDVI as a vegetation index across every month of the full year. And in doing so, you get the full phenology of vegetation. And you sort of let the algorithm figure out which parts of that is useful. In the context of cropland, it's for example very useful to get the times of harvest where cropland looks very different from surrounding vegetation. Also getting perhaps peak of season and a few observations like that. Now, I think there are kind of different approaches to this. One is to do what we did, which is just include all of the observations and let the algorithm figure it out. You can also try to reduce this data to seasonality metrics, like, for example, length of season, difference between peak and well, basically all kinds of measurements that would indicate essentially how the season changes over time, or how these land covers change over time. Yes, and so I'm not quite sure if it's so important exactly which index we're using here, as long as it's one that sort of more or less accurately captures these the seasonal variability. NDVI seems to be by far the most commonly used, and that's also why we used it here. I think what's really important is to get a good temporal range in your index when you're trying to differentiate these land cover types like we were doing.
Certainly. Thank you for that response, Victor. We have a question. Yeah, hello, thanks for the very interesting talk. We'll definitely check out the paper. The geocoding of conflict in ACLID is to the nearest big town or settlement. And I think often this might be greater than the 10 to 15 kilometer threshold you use for detecting the conflict. Do you have any idea of how big of an uncertainty this introduces to your 17% estimate?
That's a very good question. Thanks for that. I'm unmuted, yes. We know we have not quantified what kind of uncertainty that would introduce. ACLID has these sort of a three-step classification on how spatially accurate the data is. And if I remember correctly, we did a filter on that. Now I'm a little bit unsure, I have to check up in our notes here. But I think we filtered out some of the most imprecise points. And it could very well be, as you say, that it is reference to the nearest settlement. Although I do have a feeling that some of it was also geo-referenced to non-settlement areas, but you might very well be right. So no, we don't have that quantified, but it could certainly be that has somewhat of an impact on these estimates. That's true.
Fair enough. We've got a question from an Ariana Sika. Hi, Victor. Very interesting presentation. I was wondering if you know more about the drivers of cropland reduction. For example, did conflict directly have an effect on it? For example, burning fields. And did people generally abandon the areas with armed conflict? Did their resources reduce and thus prevent them from cultivating?
Right, thanks for that question. I mean, you can only respond to that anecdotally from sort of the research we've done around this study, or sort of the reading and literature reviews we've done. It seems that what is very often the case is that there's security concerns preventing farmers from reaching the fields. So what we often see is that there's this contraction of cropland towards the center of a settlement. So people simply don't dare to venture too far from the homestead. And I think this could at least explain some of the reason why conflict is reducing these cropland areas. Of course, there's all kinds of other things that also influence it, but I think that's part of the explanation.
All right, and it looks like we have one more question. If anybody else has any burning questions, please enter those into the chat box so we can get to them. But our last question for now is from an Anas Baramune. And have you considered using net primary productivity to have the spatial data regarding food production?
Right, that reminds me of one of the other questions that I actually forgot to answer now on food production. No, I have not considered that. So maybe just a follow up here is that the idea here would be to estimate food production, and in the context of this study, perhaps contribute a little bit to the last part of it on estimating the kilocalorie losses. If that is the case, then that does sound like a good idea, because what we're basing these numbers on are these statistics that are quite general. So it's quite general statistics on how much yield you would expect for this particular region on average, how many kilocalories you would expect from certain crop types and such. So it doesn't really take into account changes over time and such. So if there was an indicator on productivity that would improve the estimates and these yields and kilocalories, then that would also sort of strengthen the findings here. But no, we didn't do that. No.
Just very brief also reflection on that. We got the good bulletins, so the World Food Program makes the bulletins and trying to record the crops. The challenge also with this type of the areas with the smallholder farmsteads, particularly in Africa, is that it's like entire intermix that we have in play the size of the fields with some shifting cultivation. Then we have different crops. It could be sorghum, it could be cassava, it could be other crops with a different productivity. And what Victor mentions also, that it could be a really interesting way to dig further how we can measure remotely. Because again, in our case, we had a great privilege that we had the data from the ground. But how many areas where we don't have this data in the ground, which exactly in the severe condition? And this opens a really interesting direction, also linking the productivity and the conflicts, but also agricultural land abandonment. And how does this impact the food security? I quickly see the list of the participants, and among the participants, I see Hayin, who is working on these topics also in the Middle East and had experience in the Caucasus, but also Xiaopen Son from University of Texas, if I correctly pronounce, who just also published a nice paper in Nature Food on a similar topic with the different techniques, and also looking about the impacts of the abandonment and the conflicts on the food security. So that gives really a great way to look at this abandonment from the angle of the food security, which was not done that much before.
Thank you for those insights, Sasha. It looks like we've gone through all the questions, and so I'd like to bring this session to a close. On behalf of NASA Land Cover and Land Use Change Program, I'd like to thank our speaker, Dr. Olson, and our fellow panelists, Dr. Olofsson and Dr. Kristupov, for their contributions. I'd like to thank all of our participants for attending the webinar, and we hope that you find the information presented here both useful and valuable. We encourage our participants to send us any questions or comments about the webinar and about future webinar series. A link to today's webinar session will be posted on our website, and this is useful if you want to review any of the material that you might have missed or would like to go over again. We hope to see you all in the next webinar, and I believe that next webinar series will begin next month. Information about this will be posted on our website. And thank you again, Mr. Olson, and thank you all for joining us. I hope you have a great day.